In this video, I'll be looking at classifying numbers. And so we're going to go ahead and start with the most basic set of numbers and then go from there. So these are the numbers we use in an algebra course, and later on we'll add more, actually very soon. So first of all, we have the natural numbers, which are basically the counting numbers, 1, 2, 3, and so on. If you add 0, now you have what are called the whole numbers. Integers will include all the whole numbers and then the opposites, the negatives. And so one thing I want you to notice is, for example, the number -2. Oh, actually, let's not do that one. Let's say the number 2. Notice the number 2 is a natural number, it's a whole number, and it's an integer. And so most of the time, numbers are part of more than one set. Not necessarily, but quite often that's the case. So that's not a surprise. And then finally, we have rational numbers. I should say next, we have rational numbers. A rational number is a number that can be expressed as a quotient of two integers. We call these fractions. Ratio, fraction. So basically, any number that can be written as a fraction is considered a rational number. Now keep in mind, all the numbers we've discussed, if you write them over 1, we can say, yeah, those can be written as a fraction, and so every number we've discussed so far is part of the rational numbers. All right, so notice here, it says in decimal form, any numbers to the right of the decimal either repeat or terminate. So this is true with rational numbers. So an example of a terminating decimal would be 0.75, which is equal to 3/4. An example of a repeating decimal would be 0.416, where the 6's repeat. And so 5/12, or well, actually in decimal form, you can see the decimal part repeats. So with fractions, when you change them to a decimal, you're either going to have a terminating decimal or you're going to have a repeating decimal. Finally, we get to irrational numbers. Well, those are the ones that are not rational. So some examples are pi, which we know is about 3.14, and then it keeps on going on, and there's never any repeating pattern. And you can see, well, actually, if you find the square root of 5 on your calculator, again, you'll see that there's no repeating pattern. This is another example where you're not seeing any pattern being repeated. Even though on this decimal here we have a pattern, it's not the same repeating numbers. And so that is also considered irrational. All right, so I'm going to go ahead and fill in the diagram here. It's a nice visual for what we're doing. So first of all, we have our natural numbers, 1, 2, 3, and so on. And then with the whole numbers, now we're adding 0. With integers, now we're throwing in the negatives. So I'll just put a couple of integers in here, a positive, a negative, and 0. And then rational numbers, anything that can be written as a fraction, so 2/3. Or in decimal form, we could have something like 0.12, where we have a repeating decimal. Let me put an improper fraction, 5/4 here, and a terminating decimal, 1.25. And so these are all rational numbers. The most famous irrational number would be pi, square root of 2, or other square roots of numbers that are not perfect squares. Like the square root of 9 would equal 3, so that's not irrational. But if you're not taking the square root of a perfect square, then it'll be an irrational number. And let me just give you one more. How about 5.454554555, and so on. So the idea here is it's got a pattern, but notice there are no digits that are repeating. to the right of the decimal, and so this is considered irrational. All right, so let's go ahead and do a couple of problems. In fact, I would encourage you to try these problems and then watch the video. All right, so natural numbers. So as you look through the numbers here, 3 is a natural number, and notice the square root of 36 is 6, and so the square root of 36 would be considered a natural number when it's simplified. Either way, it's considered a natural number. Now, for the whole numbers, we're going to have the same numbers, but we're also going to throw in 0. For the integers, so again, we'll have the same numbers, and then we're also going to throw in the negatives. So we're going to have -1, 0, 3. Notice -8/4 is equal to -2, so that's considered an integer, and the square root of 36, which we already had. So in letter D now, we're supposed to include all the rational numbers, so that's going to include everything we just got, plus a couple of others. Let me use a different color here. So notice if we have anything that can be written as a fraction, or it's either a terminating or a repeating decimal, so we're going to add 1.285, which is terminating. We've got -3/5. How about 5.94, where the 94 repeats, so that's a repeating decimal. Notice this one here is not, it has a pattern, but it's not repeating the same digits. And so it looks like we're good there, so let me go ahead and write those in. So we've got 1.285. I'm just going to go from left to right on the list here. -3/5, -1, 0, 5.94, where the 94 repeats, -8/2, and finally the square root of 36. Irrational numbers, well, those are going to be the other ones. They're not rational. So we know we're going to have, let's see, the square root of 2. We've got that long number, 4.2122, 1222, and so on. And then finally, don't forget this one here, pi over 2. Anything that's got a pi in it is going to be irrational. If you divide an irrational number by 2, it's still going to be irrational. And finally, the real numbers include all of these numbers. In fact, that's what our square up above represents, is the set of all real numbers. And the two major groups are the rational numbers and the irrational numbers. On number 2, it says, list the numbers that are rational numbers but not integers. Well, let's see. Just look at irrational numbers, and you've got 1.285, -3/5, and 5.94, where the 94 repeats. All the other numbers on that list are rational, or I'm sorry, are integers. All right, and that's the end of this video.